This module is about generating the random numbers with a computer. I have to say it's pseudo-random numbers, but for the purpose of our discussion it's not that important. So generating uniform distributed random numbers is easy on any software, including Excel. So in Excel you have the function called rand. Right, okay. Uniform random numbers from 0 to 1, they come from uniform distribution, which means with equal probability you can get any number between 0 and 1, like 0, 1, 0.5, 0.3, and so on. How do we generate in Excel? So let's take a look at Excel page here. I'm going to increase the font a little bit. So what I'm doing here is very simple, right? I'm counting the trials, and just for this to get a better precision on histograms, I'm using 1000 random numbers. So I'm generating 1000 random numbers. How am I doing it? Very easy, right? I'm using the rand function from Excel. Any software will have an analog of this function, and oftentimes it will be called rand, or sometimes it's called RND, uniform random numbers, right? So in this table I am building the histogram manually. So you know, in Excel there is a histogram function which you can call from if you install the analysis toolpack, you can call data analysis, and in data analysis you can pick the histogram. But I wanted to do it programmatically, because that one you have to go through a couple of manual steps. So here what I'm doing is I'm building the histogram manually. So first I build cumulative distribution function, and if you remember what is a cumulative distribution function, right? It's a probability that a random number will be lesser or equal to x. So your cumulative distribution function fx, the definition is that it's a probability of a random number being lesser than or equal to x. And I'm precisely implementing that logic here, right? So if you look at what I'm doing here, I'm just getting the count if. So I'm counting all the numbers which are less than 0.1, and my bins are running from 0 to 1, right? So the first bin would be all the numbers between 0 and 1, 0 and 0.1. The second bin would be all the numbers between 0.1 and 0.2, and so on. How do I implement the function? Here it's very simple, right? So I get all the numbers and then count them if they're lesser than or equal to 0.2. Then I'm dividing it by 1000 because I have 1000 trials. So here is my CDF. I'm drawing the CDF on this histogram. It's a histogram of CDF, and you see it's a uniform distribution, so it'll go from 0 to 1 in a in a linear fashion, right? I can press F9 several times just to show you that this works pretty well, right? So your function is moving a little bit, CDF. It's not ideal line, of course, because we have 1000 numbers and they're random. So they are not perfectly distributed 100, by 100 count in each bin, but it gets pretty close, right? Then in a column G, I am drawing the PDF, probability distribution function. This is uniform distribution. In mathematics, it's a continuous distribution. Obviously, this is a computer, so when you call rand, it's not a continuous distribution anymore. But we can forget about it for a second. we usually it doesn't matter, right? But in a computer, there is no true continuous variable or continuous random number for that matter too. Anyhow, forgetting about that complication, we can build a PDF. How do we build a PDF? PDF is very simple, right? The difference between CDFs, that's what's going to be your PDF. Probability distribution function. Well, I guess I'm forgetting probably to I'm forgetting to scale it by the bin size. I should have done it, but I'm not doing it here, so please forgive me. Okay, well, maybe I'll do it. Why don't I just do it so that I don't have to ask for forgiveness? I'll just divide it by 0.1. Okay, so then I'll show you the correct formula in the end. 0.1, okay. Let me see. I think I'm doing it right. Nope, I'm not doing it right. I have to divide this by 0.1. Okay, now I'm right. I should be right. And this one should be scaled by 0.12. So now we get 100. Right, so what are we seeing here? Again, very simple, right? Let me scale this so that it's from 0. Right, okay, good. So all I did was just called uniform random numbers with Excel's built-in function, and as I said, you can do it with pretty much any software, Python, Java, C++, whatever, and any kind of software will do it. Now, what if I want to generate the random number not from the uniform distribution, but from something else, from some other distribution? And that's where there's a little bit of a problem sometimes, especially if you're working with something unusual, right? With something which is not very popular, with some probability distribution which is not in every other software. And in case of Excel, that would be everything else but uniform. So there is no simple one-call function, for instance, to generate Bernoulli or Poisson or Gauss or Gaussian, meaning normal distribution, or binomial. Nothing. In Excel, you only have uniform distribution. Right, but again, this problem can arise not only in Excel, but even in a sophisticated statistical package if it turns out that you need a probability distribution, which is not very popular and no one implemented the random number generator for it. So what are you going to do in that case? Well, in that case, you can use this very simple method I'm going to show you. It's not the most efficient sometimes, but it almost always works. It almost always works as long as you have an inverse CDF, cumulative distribution function. Sometimes even without having inverse distribution, you can sort of build the inverse distribution to make it work. And I'm actually going to show you how we can use the cumulative distribution function without having inverse cumulative distribution function and generate the random numbers. And we're going to do it with Excel. But before we do it with Excel, with Poisson, before we do it with Poisson, why don't we do something very, I would say, intuitive, right? We'll understand all these formulas, but we'll first do something very intuitive and simple. How about Bernoulli, right? So what is Bernoulli? Well, we studied Bernoulli or you studied Bernoulli at some point in your career, I hope. Uh, with Bernoulli, you have two outcomes, and usually or often we denote them with 0 and 1. It could be heads or tails if we're doing a coin toss, and so on. So let's denote them with zeros and ones. So imagine now we want to generate random zeros and ones, or random heads and tails. How would we do that? So one way to do it is, of course, to use the ideas which I was just talking about, right? So give me a second. All right, so we could have the uniform distribution and do something with its Bernoulli distributions, CDF or inverse CDF. But before we do it, let's look at a very intuitive, simple way of generating heads and tails or zeros and ones. Why don't we do this? We call the uniform distributed random number from 0 to 1, and then if it's less than 0.5, we will generate 0. And if it's greater than 0.5, we will generate 1. So how can we do that? Well, with a simple instruction, we will say if uniform is less than 0.5, right? I hope you can see it. I want to make it a little bigger. Right, so the formula here is very simple. If uniform distributed random number, and we're picking it from uniform sheet here. You don't have to do it. You can actually put it in, call it in place. But I'm calling it from uniform random number sheet. So I'm just checking it. If it's less than 0.5, my if will return 0, and if it's greater, it'll return 1. That's all. And then I generate 1000 random numbers, the same way like I generated before, right? Checking 1000 uniform numbers for whether they're less than 0.5 or greater. And then I'll build the CDF in column F, and well, in this case, it's usually called probability mass function. This is a discrete distribution, so they're called PMF. So on top I have PMF graph, and at the bottom I have CDF, cumulative distribution function, and probability mass function. So you see that it's approximately 0.5. 50% chance that it's 0 and 50% chance it's 1. I'm going to press F9 several times. You see it moves a little bit, but by not much. Right, I have 1000 random numbers, so depending on which numbers what was that set of 1000 numbers, my probabilities can be slightly off of 0.5, but they're pretty close. You see they're not moving a lot. Very close. So maybe I will change the scale here, make it closer to 0.5 so we can see the change closer, right? Okay, let's like that. So I'm going to press F9 again several times just to demonstrate that we are very close to 0.5. And CDF is obviously what we're going to see, 0.5 and then 1, so it's like a linear. So this is a typical CDF for Bernoulli distribution. Right, so this was very logical. Right? You get the uniform random number. If it's less than 0.5, you're going to say it's 0. If it's greater than 0.5, you're going to say it's 1. So interestingly, we can use this exact method to generate almost any other distribution, as long as we know their cumulative distribution function. So now let's see how it works.